So this is a very well-known problem, asked in many interviews different times. Some of you might have even heard of it. So this says that you have been given a two-dimensional matrix, okay? And in this matrix, any cell either has a value 0 or it has a value 1. So it is a binary matrix of zeros and ones. 0 means water. 0 means that that particular cell which has a 0, it contains water, okay? And 1 means that that particular cell which has 1, it contains land. Now it says another thing, that two cells are adjacent. Two cells are adjacent if and only if this is your I comma j, and let's say there is a cell that shares a side with it. There will be 4 such cells. Then those cells are considered adjacent. Apart from that, those cells which are diagonal to it, which share a vertex, those would also be considered adjacent. So the maximum number of adjacent cells which any cell I comma j can have is 8. 3 up, 3 down, and 1 here and 1 here, right? So this is how adjacency is defined with respect to any cell. So what you have to do is that you have to count number of islands, and I hope all of you understand what is an island. So island is something which contains land and is surrounded by water from all the sides, okay? So let's take an example. So let's say I give you a matrix. Yeah. So how many islands do you see over here? Just go by the definition of land and water and try to tell me how many islands are present here. Do others also see that there are 5 islands over here? So if we understand that, how do I go ahead? So see, some of you have started talking about connected components. Now you know, many grid problems that you will have, you have to model that grid problem as a graph problem. So many a times it happens that a grid problem can be modeled as a graph problem and then it can be solved. Now you know, here how you can model it as a graph problem. The moment island is being talked about, then connections are being talked about, that how many cells having 1 are kind of connected to each other in an adjacent manner, okay? So I can say that a particular cell, let's say this is my I comma j, it can be connected to how many different cells? Can somebody talk about that? In the worst case, it can be connected to 8 different cells, and those 8 different cells will be this one, this, and this, right? So in the worst case, there can be 8 different cells which can be connected to a particular cell, right? Now, the logic of the connection is not just dependent on something like these things, but it is also dependent upon the fact that I have to basically figure out islands. So islands means that lands linked to each other. How many lands are there which are linked to each other? So when I assume each of these cells to represent a node, let's say each of these cells are representing a node, then I can say that, hey, I have a connected component here, because if this is a node and this is another node and this is another node, then they are all connected to each other, okay? And then I have this one also, right? So I can say that this is a 1 which is directly connected to this one, and this one is connected to this, and this one is connected to this, and this is connected to this. So this is one connected component that I have over here. I have another connected component here also, where it is basically looking like this. And then I have a connected component here, here, and here. So 1, 2, 3, 4, and 5. So there are 5 different connected components that are out there in this case. So this is what I have to basically, this is a question that I have to solve. I have to figure out that how many connected components are out there. So how do I actually go ahead and solve it? So now this looks like that in a graph world, if let's say I was given a graph where this had a label 0, this had a label 1, 2, 3, 4, 5, 6, and let's say I had adjacency list, then I could use this approach. I would just call DFS from main function and count that how many times I have called it, and my job would get done, right? But here what do I do it? Here you tell me one thing, do you really need an adjacency list over here? Here your adjacency list is this definition. This definition that I comma j can be connected to these 8 only is your definition of adjacency list. So whenever you are at a cell I comma j, all that you have to do is you have to check up, down, left, right, diagonal, 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 diagonal. So you have to check the 4 up, down, left, right and the 4 diagonals. And if the cells exist in those directions and there is a value 1 over there, that means that, hey, there is a node which is connected to 1. So you would call a DFS over there, right? So what you would actually do is, let's say you are starting from here. Let's say you call DFS first at this node. Once you call a DFS at this node, then what you would do is you would check for left. Left doesn't exist, right exists. So you would call here. It has to exist. So let's say you are checking for this, which is I comma j plus 1. So first thing, this has to be a valid cell, and second thing, that this cell should not already be visited in the DFS journey, and it should also have a value 1. Then only you would make a DFS call over there. So in that way, if you make a DFS call here, you visit this, this, this and this. And now the next one that you have not visited is this. So now when you make a DFS call here, you visit this, this and this. Next one not visited is this. Once you make a call here, you just visit this, and then you make a DFS call here, and then you make a DFS call here. So 5 DFS calls, and that's how you get your job done. So this way you can go ahead and you can very easy solve the problem. Now few things to talk about here. You have to check whether a particular node is visited or not. So how will you check that, whether a node is visited or not? Yeah, so one way is to mark the cell as 0, and I'll talk about that way later. What I can say is that here any node can be denoted by 2 things, which are I comma j. So I will have an is visited matrix of m cross n, and then I will initialize all these values to false, saying that none of the cells have been visited till now. And the moment you visit a cell I comma j, then what you should do is you should convert is visited of ij to true the moment you visit it, and then you call all the direct linkages of it in all the possible 8 directions. So this is one simple way that you can have to get your job done. So that you can always do, right? Another way is that once you have visited a cell, okay, then convert it to some other value, okay, so that you don't have to visit again. What you can do is, one very simple thing that I can do is, once I have visited a cell, then I can convert that value into 0. Converting this value into 0 will ensure that once this is converted to 0, and let's say DFS call comes here, it sees that it is connected to this, but it will not call that, because it calls only if the value over there is 1. So what is this going to ensure? This is going to ensure that you will not need that extra space. So in this process, you need extra space of m cross n, but if you cleverly manipulate the cells to some other value, then you do not need that extra space. So this is one simple thing that you can use. And now again, because this is a disconnected graph, so you cannot make a call anywhere. So what you have to do is you have to traverse all of these, and only if you see that, let's say there is a cell which has a value 1 in it, then only you will start a DFS from there. Okay, so if you actually write your actual DFS logic, how is that going to look like? So you have a DFS function that takes I, that takes j, and this is a void. Okay, and what is the first thing that you do? So whenever you are at particular array ij, then you are going to change this matrix of ij to 0. Changing this matrix of ij to 0 ensures that you will not visit it again. And then what you are going to do, you are going to check every neighbor. So let's say first you check for the right neighbor. So first you will check if is safe ij plus 1. So this is safe will check whether this index actually exists or not, and you can write this is safe method. That is the first thing. And second thing that you want to check is that there should be a 1 over there, because only if there is a 1 over there, then that is a part of island, so I'll call it. And 1 will not be there if that was already visited in this DFS journey. Okay, so if I just have this much object that if that is safe and matrix of ij plus 1 is 1, then only I'll start a DFS call from I comma j plus 1. Now the same logic that you have written for this cell, you can write it for this, everything. So this thing has to come for 8 times over here, right? And that's how you get your job done. So now this will ensure that once you have done a DFS here, all these would have become 0. And now the next one that you will get will be that one which was not a part of this connected component. So now you can have your for loop based logic here and keep incrementing this count, and that's how you all get to your answer. So I think this final part all of you can do. Just iterate on this main function, just iterate on this 2D array for I varying from 0 to m minus 1, for j varying from 0 to n minus 1. And what is the first thing that you do? You check if that cell is was a part of previous connected component or not, and is that a land or not. So if matrix of ij is 1, then only you would want to start a DFS from there. So you would start a DFS from I comma j and you would do your count plus plus. That's how your job is done. Okay, anyone who would like to talk about the time complexity of this? So I believe you are assuming that this is an n cross n matrix. So basically the thing that you are doing over here is that you are doing DFS on this graph, right? Your graph is this plus this plus this plus this plus this. And what is the complexity of DFS on graph? It is order of v plus 2e, right? Order of v plus 2e, right? You have to come up with v and you have to come up with e. Can you tell me what can be the value of v in the worst case? Maybe n square, because each of the cell is being treated as a particular node, right? So there will be n square different vertices out there in the overall graph. And how many edges? So if you try to understand, if let's say there is a 1 over here, and this can be connected to this. So how many edges, what is the maximum number of edges that can emanate from a particular vertex? 8, right? 8 is the maximum number of edges. So in the worst case, the maximum number of edges that you would have would be 8n square. So this will be like 16 n square, and this will be n square, which is 17n square. You can approximate this entire thing to order of n square. So this way I can say that the entire intention that I had was to convey you that do not blindly say order of m into n or n square. Come up with the worst case value of vertices, come up with the worst case value of number of edges, and then do this calculation and then tell the answer, right? Because technically we have proved how the complexity of DFS is v plus 2e, right? So this you can do, and that's how you can go ahead.